Good evening, everyone, and thank you for introduction. And today I'm going to talk about two complementary methods: Bayesian classification, or in general like Bayesian modeling, and active learning, and an application of these two methods in continuous flow crystallization. So I have organized the talk like this. I'll start with a motivation, and then I'll introduce the background, which is the application of the methods. I'll also briefly explain the computational framework, also giving some theoretical background for those who are not familiar. Then I'll talk more about the proposed method that we use. I'll also demonstrate it using a case study, and then I'll go through the results and conclusions. So to give a general but important motivation, so last few decades saw an enormous increase in the speed of computing. This has made a lot of things possible, including the recent boom of AI. One important consequence is that now online decision making is possible. So by online decision making, I mean real-time decision making using computers. The extent of human intervention needed there to decide what to optimize or when to optimize is a different story. But the important thing is that online decision making using a computer in real time is possible now. So for this, in order to make the decisions reliable, we need to develop models with good predictive accuracy. Also, since if we are applying these models on a real-time process, we have very limited data sets. So using those limited data, we need to develop this data-driven models in real time. So the challenge is we really need to design the data to train these models carefully. So we need to design the most informative data set so that we don't need big data. One of the methods is to use probability models with satisfactory confidence. So the probability models is by modeling a probability distribution of the data, and it will actually give a certain degree of confidence to our belief regarding the process. So in this talk, I am actually going to talk about the development of such a probability model with an application that I am going to explain in the next slide. So pharmaceutical industries are relying on process analytical technology for manufacturing of drug particles. So this technology is actually a combination of online analytics, automation, and machine learning methods recently. But actually the application of such frameworks are limited by big data. So we really need to develop data efficient machine learning models so that we can integrate those methods to this platform to make this really working for the manufacturing of drug particles. From the application point of view, which I'm going to talk in this presentation, is really regarding the continuous manufacturing of API particles. There, fouling is one of the biggest bottleneck. As we are handling suspension within the flow systems, there is always a greater chance for the particles to get settled down, and this can actually block the entire system, and it will be very expensive then to clean up everything. So in this talk, we are trying to develop a Bayesian classification model to identify the feasible operating space which is free from fouling for a continuous flow crystallization platform. The full computational framework of the platform looks like this. So we always start from a DOE method, which is used to design initial or preliminary set of experiments to train our machine learning models. So we anticipated that when we design these experiments, for this we can use latent hypercube design or factorial design. So these are like purely statistical sampling methods. We anticipated that when we perform these initial experiments, some kind of fouling could happen. So this actually gives the possibility to label the data set as 0 and 1 based on if the experiments has caused in fouling or it results in a smooth operation of the process. So using those labeled data set generated from the first DOE experiments, we can perform a classification to identify the fouling free regions. Then the further experimentation can be actually concentrated in this region, and the further data set actually developed in this region can be used to develop the regression model that relates the important process conditions to the quality attributes of the drug particles generated. So that's the whole framework. But in this talk, I am actually focusing on this classification approach, how we can actually develop a classification model in closed loop to identify the feasible operating region of this process. So in general, we used Bayesian classification and active learning. So we use Gaussian process model as the latent function for the Bayesian classification. So the basic idea of active learning is that we start to gather data from the initial DOE experiments. We build our classifier model. Then we see the performance of the model on the test data set. If we are happy with the performance, we can employ the model to screen the design space and to obtain the fouling free region. If you are not happy with active learning techniques, we will actually look at the uncertainty in the predictions of the classifier model. And then we use this information to actually design the next experiments so that most informative training data can be generated to further train the model. And this can be continued in closed loop until we actually develop a good model, a model with a good predictive accuracy. So those who are not familiar with the theoretical background of Gaussian process model for classification. So I'm going to explain like two cases, like binary and the multi-class. So binary classification is can be understood based on an event such as tossing a coin. So when we toss a coin, we have only two possible outcomes. So just like similarly in binary classification, we have like two possible outcomes, a 0 or 1. So in this particular case, 0 means a condition which results in fouling, and 1 means we have a non-fouling condition. If we have n number of experiments, or if we have n trails of a coin, so the number of success or number of times we see a head, or similarly number of times we see a 0 can be distributed by a Bernoulli distribution. And now, so each outcome is with a certain relative probability. So from the latent space, from the GP space, we can actually obtain the relative probability to obtain each class using a sigmoid transformation, which actually transforms the continuous function to a probability space. Similarly, in the multi-class case, imagine throwing a dice. So we have more than two outcomes, each outcome with a certain probability. So similarly, for the multi-class classification, we may have like a situation where we have labels as 0, 1, and 2 corresponding to different cases, different class types. So in that case, the number of times we observe one of the outcomes can be defined as a categorical distribution. and each outcome will happen with a relative probability that can be obtained from the continuous function space by using a softmax transformation. So once we have the GP, the model training and the active learning methods are performed by solving numeric optimization problem. So here suppose we have a data set, a labeled data set with U's and Y's. So here U stands for input. Most of the cases there are these are vectors, because we have more than one conditions that define a particular experiment. And Y's are the discrete labels which define if the condition is following or not. In this case it can be 0 or 1. Once we have such a labeled data set, we can actually define the likelihood, which is the probability of obtaining the data given the input that define the outputs y and a certain parameters. So assuming the data sets are independent, the likelihood can be obtained as the product of like probabilities, and when we train the model, we try to find out the hyperparameters which actually maximize the likelihood function. So this will actually give us the values of the hyperparameters which are optimized after the training of the model. So now the question is which experiment need to be designed next, so that we can actually generate the most informative data to further train the model. For this we can use the active learning method, which is again another optimization, but here actually the decision variable is the input space. So we are actually trying to maximize an objective psi of the posterior probability function of our model. In the literature, usually we define psi based on two types of objective function. One is we can use the probability values. For a binary classifier, it looks like p times 1 minus p, where p is the probability of an input belonging to a particular class. So if p is 0.5, 1 minus p is, which is the probability belonging to the other class. In this case, that label is very uncertain. So most probably that point will actually lie near the boundary separating the two classes. So if we actually maximize this objective function, we more likely sample the region in the design space which is close to the decision boundary separating the classes, because that's the region where the model might be very uncertain about whether that point belongs to the label 0 or 1. So that's the probability based criteria for psi. There could be also uncertainty based criteria, where actually we use the uncertainty in the predictions of the latent function value to decide to design the next condition. So we sample the points where this uncertainty is largest. So that point the model is very uncertain, because maybe the model has not seen a lot of points in the input space. So when we do that, we will get most informative data to train the classifier model. One limitation with this approach is that it is based on the location of the predictive function that separates the two classes. So the convergence can be slow when we use the probability based approach. On the other hand, when we use the uncertainty in the latent function space as the criteria to design the next experiment, it can become explorative, in the sense it can take more experiments. So to overcome this, we are proposing a new active learning method which is based on the propagated uncertainty in the probability space. So here I'm explaining the case for binary classification. So in the binary classification, we use one Gaussian process model as the latent function, which will actually give us a continuous prediction like y1 So we can use this y1 and apply a sigmoid transformation to get the corresponding relative probability p1, which is the probability belonging to one of the classes. So the probability for the other class is 1 minus that probability. So that's the reason we only need one GP for binary classification case. Along with the prediction of the latent function values y's, GP will also give us the uncertainty around this prediction, which is delta y. So if you want to propagate this uncertainty into the probability space, we can use the linear error propagation theory. If you use that, we can actually propagate the uncertainty from the latent function space to the probability space, and the uncertainty in the probability space is used as the new objective function for active learning. This can be also obtained for the multi-class case. So in the multi-class classification, for example, if you have 3 classes, we have 3 GPs corresponding to each class, and the predictions of the GPs in the latent space can be converted to the relative class probabilities by applying a softmax transformation. And then again, similar, we can propagate the uncertainty in the latent function space to the probability space using this rule. And we can actually define the new objective function based on this uncertainty in the probability space. So to demonstrate this new approach by also comparing with the previous active learning methods, I'm testing this. We have tested this on an in silico case study, where we, for a binary classification case, where we have 2 labels, again 1 and 0, 1 corresponding to the feasible experiments and 0 corresponding to the unfeasible experiments. So we performed actual experiments, and using the actual experimental data, we validated an SVM model. This model was assumed as the true model for the in silico case study to generate more data. Meanwhile, the Gaussian process classifier model was used as the classification model to identify the feasible operating region. 10 new experiments were actually generated using 3 different active learning methods. So one is based on the probability based, where we only use the probability values. One based on the uncertainty in the latent function space, and one based on the proposed method, which is the propagated uncertainty one. So if we look at the result, so this shows the design of experiments in each of the 10 iterations, where this star points denotes the optimal experiments designed. And so by maximizing the probability based objective function, so it's a typo here, so it's not the prediction variance, it's the probability based objective function. So here we can see that in each iteration, it picks the point where this objective function is maximum, because that's a point where the model is very uncertain. So if you also see this in the probability space, we could see that the model most of the times picks the optimal points in this green region, where the probability is 0.5. So the probability is near 0.5 means those points are the points near the decision boundary separating the 2 classes, where the model is uncertain whether it is an actual 0 or an actual 1. Similarly, this shows the evolution of the experimental design using the prediction uncertainty in the latent function space. So here also the model designs experiments where this uncertainty is largest, so in this red region, and the corresponding design in the probability space looks like this. So here the the point is that the model also picks the input space where the probabilities are either very low, like close to 0, or close to 1. But actually the model, so when the probability is close to 0, that means the model is certain about one of the class predictions, and also when the probability is high. So when we only look at the uncertainty to design the new conditions, maybe it's becoming explorative in the sense that the convergence can become low. Whereas if we look at the new proposed active learning method, again it designs the experiment where this objective function is maximum. Again, there is a typo. This is actually the prediction variance in the probability space, not in the function space. So this is telling us that the optimization worked quite well because it was a maximization problem. But if we analyze the result in the probability space, here we can see that most of the time the model again picks the point in this green region where the probabilities are like between I would say 0.6 or 0.4. So those are the points like the model is very uncertain about the labeling. Yeah, this again shows the active learning the experiments designed using active learning using the proposed method. As we can see, most of the time it designs in the region where the probability is close to 0.5. So to conclude, when we want to integrate ML models in a PAD framework to assist real-time manufacturing processes, first of all, we need to carefully select the model which do not need a big data. Then we also need to carefully design the experiments to generate more data in closed loop to train the machine learning models. So here we have proposed a new active learning method to generate informative data set to train a classifier model, and this was applied on a continuous flow crystallization case study. And the advantage is that we can develop a more reliable classifier model using small data set, and this can then used as a decision support tool in the real-time manufacturing platform. It also streamlines the subsequent optimization because it eliminates the region where there is fouling, because when we actually measure the particle size in those regions, it is also affected by the fact of fouling. So constrained optimization of API particles can be also designed based on the feasible region identified using the classifier model. Yeah, that's all. Thank you. If you have any questions, I'm happy to answer.